Robin Hood Radio welcomes you to David Freeman's Science Insider with your host, the senior science editor of the Huffington Post, David Freeman.
Welcome back, everyone. Today it's my great pleasure to welcome to the show one of the nation's best-known theoretical physicists, Professor Lisa Randall. Professor Randall's been a professor at Princeton and MIT. She's now at Harvard, where she's doing pioneering research in particle physics and cosmology. She's also the author of best-selling books, including Knocking on Heaven's Door, which came out to great acclaim in 2011, and a new book called Higgs Discovery. So welcome to the show.
Thank you for having me here.
So I have a lot of questions I want to ask you, but I want to start with some recent news. A few weeks back, there was this big discovery that scientists at the South Pole had discovered evidence for cosmic inflation. So what exactly is cosmic inflation, and why were all the physicists so excited about this?
So basically, everyone's heard of the Big Bang Theory. And Big Bang Theory describes a relatively slow evolution of the universe. It expands, it cools down, and as it does so, things start to happen, interesting things in the universe. But there were puzzles about the Big Bang Theory. It wasn't the entire story. And most of those puzzles had to do with initial conditions, how things were at the beginning. They just seemed too puzzling to believe that it was just an accident. So because of that, Alan Guth and others proposed something called cosmic inflation, which is that the universe, instead of expanding slowly, relatively slowly, exponentially expanded in the beginning. That is to say, it was kind of an explosive expansion in the beginning.
Well, that's what I always understood. I thought that the idea of rapid expansion was sort of implicit in the whole idea of the Big Bang.
Well, it depends what you mean by rapid. And one way of defining rapid is how the temperature changes as a function of time. That might not be the best one in inflation because it just goes to zero because everything explodes away. But temperature decreases slowly in a normal expansion. It goes to zero really quickly in an exponential expansion because it grows so fast. It's a difference between power law growth, if you like, and exponential, which is to say if you look at how you can also look at just the radius of the universe as a function of time. That might be a better way. And by radius, I really mean the scale factor, how far apart things are. I mean, the universe is infinite, but you can say how far apart objects are. In ordinary Big Bang expansion, they will start to expand relatively slowly, again, like a power law with time, whereas it's exponential in the case of cosmic inflation, which is much more rapid.
So that means that it kind of confirms this idea that the observable universe that we see today, the scale of that is in line with when this Big Bang occurred almost 14 billion years ago. Is that right? That matches up now?
That's not exactly the problem that this is solving. What it's solving is something more like, if you look back at the universe, that is to say, if you look at the radiation in the sky, you'll see an amazing amount of uniformity. The reason I say amazing amount of uniformity is that it's uniform even across what would have been the horizon at that time. And by that I mean, if you asked, could light have traveled from one of those points to another over the age of the universe at that time? It couldn't have.
Right.
I mean, we see them both today because the universe has gotten big, this horizon's gotten bigger. But at that time, it couldn't have. And so the question is, how could they be so similar when they never even talk to each other? But the point is, that's not true in this exponential expansion. In the exponential expansion, it all comes from one single small region.
Right.
And that's one of several problems. It also addresses the question of why the universe looks what we call so flat. In other words, if you have any kind of curvature, you would expect it to either collapse or explode very quickly. Yet we have this nice old universe. How did that happen? Again, inflation helps to explain that. So cosmic inflation, when I started off, it was this nice idea, but no one really believed it. I wouldn't say no one, there were some people who did, but a lot of people were very skeptical. Because if you actually just try to construct what we call a model, some example of how this could happen, it always seemed very artificial. It just didn't seem likely. But then there was experimental evidence, and the first experimental evidence actually also came by studying the cosmic microwave background radiation. It turns out that quantum fluctuations at the end of inflation actually drive inhomogeneities in the universe. That is to say, there's density which is not uniform. It's a very, very small amount, but it started off at the end of inflation.
So were you as excited about this as I saw some of the other physicists in the community about this discovery, or was this something that you kind of thought was going to happen, was going to be confirmed?
I certainly didn't think it was going to happen. But let me just explain very briefly what the evidence is. So the new evidence, the new thing they found, is they actually found evidence for energy density back in the early universe, which would drive gravity waves. So what they actually measured was the imprint of gravity waves.
Right.
On the so that's exciting in and of itself, if that's really what they're seeing. I'd say that, in some sense, excited is right, but I was also just very surprised. I didn't expect that they would measure a number as big as they did. In fact, if you trust the evidence from a Planck satellite, which is another satellite looking at the cosmic microwave background radiation in a different way, it's hard to reconcile these two numbers. It's not crazy out of line, but based on what they had, you wouldn't have thought that these guys would have measured it. On top of that, the number is just really big from a theoretical point of view. It's very hard to imagine what the models are that really would produce this. So for me, it's just really intriguing. It's puzzling. It gives you questions to think about. I mean, if it's true, it's extremely exciting. I mean, I want to wait to see that it really is true. But if they've really measured something, anything, even if it's not inflation, it's an exciting result.
Right. Well, another exciting result was the confirmation of the Higgs boson, which I guess we're coming up on the 2-year anniversary this summer.
It's a while ago now.
So tell us, I think the basic thing that we've heard is that the Higgs boson is this long particle that are long believed to exist, and it's been confirmed that it does exist, and that explains where other subatomic particles get their mass. So my question is, how does a particle cause other particles to have mass?
That is a great question, and the answer is it's actually misrepresented, and that's one of the things I try to address at Higgs Discovery. There's actually two very big misconceptions about the Higgs, so I'll tell you what they are. One is that the particle itself is not what gives the other particles masses. It is actually what's called the Higgs field. A field is something spread throughout space, even without particles. It's like an electric field.
Right.
You don't necessarily have a particle there. So the field is there even in what we call the vacuum, the state with no particles present. And it's that field that gives particles their masses. So in some sense, we already had evidence of the Higgs field. That was the particles have masses. What the Higgs boson does is it tells you that the mechanism by which we think this is happening is correct.
Right.
So it's sort of an appendage, but it's an appendage that tells us this is real. And on top of that, we didn't actually know that the Higgs boson would be there because it could have been other mechanisms or the same mechanism but implemented by different types of fields. So finding the Higgs boson gives us a big clue as to how that field got there in the first place.
And so this is one of those discoveries, though, where the media tend to focus, since it's very hard to understand these things without metaphors, people tend to, the reporters and editors tend to focus on the excitement level of the physicists, which was pretty high. And I was there when I guess it was July 4th, and I was up at Columbia University. They read the results from CERN. I don't know where you were. I'm not sure.
If you read my book, you'll find out I was on a balcony in Greece.
I did read your book. I apologize.
Very tedious internet connection. It was hilarious.
But tell us, though, a bit about the thing that, and I did read your book in the section.
I'm just teasing.
About the. You devote a lot of time to the Large Hadron Collider itself, which is the facility at CERN, this big international research facility for nuclear research. You talk about that. Can you give us a sense, the listeners, a sense of what exactly is the collider? I know you can go on for a long, long time, but quickly, explain how awesome that structure is.
The key is that E equals mc squared. So higher energy means you can produce heavier particles with bigger mass m. The other key is that by getting to higher masses and higher energies, you're probing shorter distances. So what this collider is something that tries to get the highest energies achievable in fundamental particle collisions. I mean, you see high energies all the time, but you want to do it in a very precise, controlled way where you have fundamental particles and all the energy is carried away by a few massive particles. And so what you have is a 27-kilometer underground ring. Protons get accelerated in both directions around that ring. And at certain points, they are diverted slightly so that they collide. And where they collide, they build detectors around it, experiments. So what they're doing is they're colliding together these protons at high energy. The reason they're round is that they can keep accelerating them. Every time it goes around, it gets a little more of a kick. And then they see what gets made. They measure everything that comes out in these experiments.
But I mean, again, I was wondering about the size. You mentioned the 27-kilometer circumference. Mm-hmm. What's the diameter of this ring? Essentially, it's that divided by pi. No. The diameter of the ring itself. I mean, the insides of it. How tall is it?
It's 100. It's buried 100 meters underground. It's not. Do you mean?
But it's like a subway tube. How big around?
Oh, you can walk in it. You can walk.
But it's
through
enormous, isn't it? It's like it's several stories high, is it not?
Well, the things that are several stories high are the experiments. right? So there are several places. So there's a tunnel that's, maybe a little bit bigger than you or I, but and then there's the actual experiments, which are several stories high, and those are enormous. And that's because they're trying to measure charge, they're trying to measure energy, they're trying to measure particles called muons. They're trying to measure everything that they can that comes out. And so these have to be big so that you can separate them. They're moving almost at the speed of light, so you really have to know what's going on.
And so before this, they collide with such incredible intensity. There was some concern, which you write about in your book, that these things were going to create small black holes, which would then gobble up the whole universe.
Can I just say, when you say there was some concern,
well,
there was
let me
some
say this:
concern among people
were dismissive.
Who didn't understand.
Well,
what
true,
was happening.
but it reminded me of the story, which you probably know about, at the Trinity test in 1945. There were some physicists there concerned
that's
that
what they were tapping into.
They were concerned that by igniting the first ever atomic bomb, that it would set the entire atmosphere on fire. And they went ahead anyway. I guess they did some calculations, said, looks good. And you guys, I don't want to dismiss what you did, but you did calculations which reassured you, correct? Was this an utterly ridiculous concern that the black holes might be?
So I think I'm pretty clear about this. So first of all, in the case of the Trinity test, there had been an incorrect calculation that made it look more likely than it was. Then they redid the calculation and it looked less likely, and that's when they went ahead and did the test. That's not to say that there was no risk at all, but they had pretty much established that there was very small risk. In this case, there really was basically no risk, and for the following reasons. One is, there's a lot of assumptions that go into these black holes. I think it was tapping into that nuclear mentality, but it's not what was going on here. One is that for this to happen, you're making not normal black holes, but higher dimensional black holes. There's a big speculation there that there are extra dimensions of space. Secondly, the energy, even if that was true, the energy still wasn't high enough to make them. That's a calculation that we did afterward, because it was just a rough estimate. Third, these things aren't truly black holes in the sense that even if they got made, they're like particles, they decay right away. You'd have to have much bigger, large objects. And by decay right away, even if it was a black hole, there's something called Hawking radiation, so these black holes aren't stable. So they don't stick around and keep absorbing stuff, which is what people were afraid of. So these are more like particles, and they decay right away. But the real nail in the coffin is the fact that these collisions go on in the cosmos anyway. That is to say, you wouldn't have neutron stars. Under ordinary circumstances, it would destroy the sun. These high energy collisions are happening in the universe. So the fact that we can observe that, we can actually ask, did these collisions do something that these black holes would be evidence of black holes? And we could see that that wasn't true. So even if you ignored all the theory altogether, it was still clear that it was safe.
But let me, not to play devil's advocate because I completely buy what you're saying, but is there, you talk in the book also, in this book, Knocking on Heaven's Door, about this idea of certainty, of giving answers and kind of being upfront and transparent about the level of certainty that you have, whether it's, as an example you give of going out to a game or something, I forget, you were talking with a friend was asking you how, and you said, well, maybe there's an 80% chance I'll go or whatever it was.
Yeah.
So you clearly had some doubt, enough to do some calculations, right? But it's like, so on some side, did you obviously felt comfortable that you were going to do something which might, in a very, very tiny risk, could result to cause the end of the world, right? Or was that just not at all part of it?
So I would put it a different way. I would say, if someone raises a risk that you haven't absolutely established, it's your responsibility to go and check. I don't think anyone actually believed this was going to be a danger. But I think it was fair for people to ask, and it was fair to be answered. And I think CERN took it incredibly seriously, and they put out a report, and they just to really show that it was very well established. And so even if you didn't know in the beginning whether or not it was risky, by the end you did know, and that's science. That's legitimate. You can just say, well, I'm never going to look at risks, and that's silly. If you know what they are and you know how to do the calculations, go look at them.
Right.
And I actually think that's the responsibility of scientists, and I'd say politicians, everyone else. Not everyone does that. So but if you can prepare for risky situations or eliminate them, it's good to know.
Well, to acknowledge it, to test it, take risks seriously, but also not to pretend that you have 100% certainty pretty much ever, I guess, in your life.
Exactly. Then you have to take into account the fact that there's not 100%, which is to say, if you can show something is not likely to happen in the lifetime of the universe, then it's probably safe.
Right. Well, talking about the universe again, I know some of the research, you've done all kinds of looking into cosmology as well as your primary specialty, which is particle physics, right? Mm-hmm. And you're among the people who believe, I guess, a growing consensus is that there is a multiverse, that we live not in a universe but a multiverse. Is that accurate?
Well, I'm not actually one of the people who talks about multiverses or works in them, in the sense that I'm less interested in things that we can't observe, and so they might exist. But in fact, I just had dinner with a friend who I was explaining all the reasons I don't care, and he couldn't believe it. He was like, "But sure, why shouldn't there be other universes? I mean, we don't know any. I mean, anytime we think that something isn't there because we haven't seen it, when you go and look, there could be lots of interesting things happening. It's just not so interesting to me if we can't actually study it, and it has nothing to do with our universe."
Well, is there any way for a layperson without the math to understand what it might mean for there to be a multiverse?
You understand it as well as I do. I mean, there's another universe that we can't communicate with in the lifetime of our universe.
Maybe the observable universe is here. The observable universe is here, and that there may be universes beyond that. But it's my understanding that our universe really is not expanding in anything beyond that. I mean, I guess it ultimately boils down to the same question you had when you were a little kid, right? What bounds the universe? How can someone explain it? Like, how do you explain to a child what comes at the end of the universe?
Well, okay. Which answer do you find more satisfying? This is the answer I would give. Which do you find more satisfying? That there's an end of the universe, or that there's no end? Neither one is satisfying.
Neither one is any good. And
exactly.
What's wrong with cosmology is that
right. So okay, to give an analogy, suppose I threw up a bunch of balloons in the air and let them all expand and let them all spread out. They'll never come back together again. They're all just spreading out in different directions. They're all getting bigger. That's like a multiverse. You have all these universes that are expanding on their own, but they're not getting any closer to each other. And that's perhaps an analogy. And I don't think it's so mysterious. I mean, if it's just saying that, the boundary of the balloon is all of space. That's it. And we're growing apart, but that's all we see. We only see our balloon.
But the problem is the balloon that we know is, as you point out in your book too, the balloon gets bigger, it expands into the space that we know about. And in this case, the balloon is
Right. So now, just for a second, pretend there's no other space. It's just the balloon, and you have exactly the same picture. And now it's the universe.
Okay. So in this observable universe, there seems to be something that's existing that pulls in on these galaxies that are out there, and yet we can't see it. It's not observable. That's dark matter, right? So what is dark matter?
Well, actually, one of the major puzzles we as scientists have today is to establish at a fundamental level what dark matter is. What we do know is that it's matter. It's stuff in the sense that it clumps together. It acts like matter. But it's different in that it doesn't interact with light, at least not at a level that anyone has observed so far. That is to say, it interacts with gravity, but not necessarily with light. Or if it does interact with light, it's just far weaker than anything else. So it's not made up of ordinary charged stuff that we know about. In other words, it's a new form of matter. It's just not the matter that we're familiar with.
But it's not antimatter.
It's not antimatter. Antimatter is charged, just like matter is charged, for example. Like a positron is charged, just like an electron is charged. And if it was antimatter, it would annihilate with matter. It really is new stuff. It's just stuff we don't know what it is yet.
But isn't it also possible that the dark matter is actually black holes, which we do know about, right?
So that's a really interesting idea that people have investigated. So they said, suppose the reason we don't see dark matter is because it's just small, compact objects that just are not emitting light. It could be neutron stars, it could be black holes, it could be just something small. So people have actually looked for that through something called gravitational lensing. Even if they don't emit light, if something emits light behind them, you would see the bending. So it turns out there's various constraints on what this can be. It's also hard at a theoretical level for various reasons, but we actually know how much total matter there should be. If the amount of matter were way off, the nuclei, the relative abundances of actual nuclei from early universe would be wrong. So given the constraints and that it's very hard to reconcile with those constraints and the fact that we haven't seen them, there's sort of only a very narrow window which is even possible, just given what we've observed. So I think most people are less optimistic about it, although it was certainly a worthwhile thing to look into.
So what is it? Is it 4% of the universe
4 or 5%, yeah.
is considered as matter that we can see, and the rest is a mixture of dark matter and
dark energy.
So what is dark energy?
So remember I said that matter clumps. It's really matter. Like matter's stuff, It's, I can have some matter here but not over there. I can have a ball that's here, it's not there. Dark energy is different. It's energy that's spread throughout the universe. It's smoothly spread throughout the universe. So it's just a background energy. Before Einstein, the absolute value of energy didn't matter. And if you took high school physics, you learned about relative energy. But Einstein taught us that absolute energy matters. And it's just some energy that's spread throughout the universe, but smoothly, uniformly, and that's what dark energy is.
And it's driving the expansion of the universe faster? Is that what it's doing?
And it's driving the acceleration of the expansion of the universe. That's absolutely correct.
So let me back up here a minute and ask you a couple of other questions. Well, one of the questions about dark matter energy, is it possible the Large Hadron Collider, LHC, in France and Switzerland, that will find dark matter or dark energy?
It won't find dark energy, but it could conceivably find the particle of which dark matter is made. That would be extremely interesting.
And would that be a bigger deal than finding the Higgs, or would it be?
It would be, in a sense, it would be a bigger deal because the Higgs, as you pointed out, was somewhat expected. I mean, people believed the Higgs mechanism was right. We didn't know it would be a Higgs particle. We didn't know what its mass would be, but it was. But if we find a particle that is the dark matter particle, and this is a big if, it would be very exciting.
So I'm going to ask you what's next for you, but first, what's next for the Large Hadron Collider? Or are you doing research with it?
Well, I do theory. I don't do experiments, so I just wait for them to turn back on. I tell them maybe what I think would be interesting for them to do in the meantime. But they are basically upgrading right now. They're making sure that they're ready when it turns on. They're going to turn on at higher energy. When it turns back on, they're going to work at this high intensity and high energy to see if they can find new stuff. I mean, no one believes the Higgs particle is all there is. The question is whether it will have the energy reach to see whatever else there is. And so that's what they're gearing up for.
And
it could be something as exotic as an extra dimension of space, like I suggest. It could be something called supersymmetry. There's interesting possibilities for what they could look for, at least.
So when does that happen? When will it turn back on?
It's about a year from now.
Wow, a lot of work to do.
Yeah.
So, and what about you? What are you working on right now?
You know, right now, because I've done a lot of particle physics, I'm actually working on dark matter. I think there's a lot of reasons to think we might make progress in understanding dark matter. There's lots of searches going on. There's lots of interesting theoretical ideas. I have a very different kind of idea where even though most dark matter doesn't interact, there's a small component that does. And I'm working out the consequences of that because it's very interesting for me because it has a lot of interesting... One thing that people don't realize about dark matter, it's really important for the structure of the universe, just how everything formed, how galaxies formed, etc. If there's dark matter that has the interactions we propose, it would be relevant for the kind of structures you see. And it could even affect the motion of the solar system. Or at least perturb things that exist in the solar system.
But for the layperson, all this stuff is kind of, wow, there's no practical application for any of this research, right? At least not foreseeable.
The application right now is understanding the universe. But I point out, when the electron was discovered, no one knew what the application of that was either.
Right.
I don't think that's something necessarily to fault anyone with. And I think we are, at this point, a little short-sighted when we think about everything, but science included. We want to know, what is this good for? And the fact is, the electronics revolution in some ways grew out of quantum mechanics.
Mm-hmm.
No one thought that was good for anything.
Right. But, as you said, the goal is not these possible end results down the line. The goal is just basically learning what the truth is.
I think it all just comes together. We learn more about the universe. We have better education. We have smarter people around thinking about these things, and it all comes together. And sometimes it feeds back into something that will be useful, and sometimes it doesn't. But that's not the immediate goal.
And to some extent, I'm guessing that you're driven by this quest for a sense of awe, right? You describe yourself as a non-believer. Mm-hmm. So does this kind of desire take the place, do you think, in some way of something that other people get through spiritual beliefs?
Actually, no, I don't. I think, I've actually debated this with people. I don't actually describe science so much as a sense of awe. I describe it as a sense of solving puzzles, answering questions, kind of what you feel like as an individual. It reminds me, I once talked to a space shuttle pilot, and I said, so what was it like? And I expected him to talk about, looking back at the Earth, and he said, oh, when you leave, it's like really rattling a lot. And, he's thinking about what he's doing. And I said, well, what does it look like? Oh, he's like, oh, yeah, it was magnificent.
Right.
But like it was an afterthought. And in some ways, you can communicate the awe and wonder, but that's not all science is about. Science is about understanding, and it's kind of a personal sense of just things making sense and fitting together and being consistent.
But you're writing books for lay people, right? So you are pulling back to kind of see how it might appear.
But if you read my books, I mean, they don't just focus on the wonder, because I don't want it to seem like it's just a religious experience.
There's a lot of science in there.
There's a lot of science in there, and and I think there's a lot of people who appreciate that because they do want to understand. Like, are you just? I mean, part of the problem with the way science is presented a lot of the time is we do just say, this is what the scientist said, but that's very antithetical to the nature of science. You're trying to really understand what were the logical connections that got you there. And that's the fun part about science, and that's also what I try to convey.
So talking about fun thing, it's interesting. As an editor, I'm always trying to imagine what it's going to be like for an intelligent layperson to read about something. So if there's something that's really awesome, it's easy. My job is easy, right?
Right.
It's difficult to explain the science and to some of these things in a way that's satisfying to someone who doesn't have the math that you have.
I use the analogy, I like classical music, but I've never really studied classical music. And if I go to a lecture or read a book about classical music, I will not get as much out of it as the composer I worked with. But I'll still learn something. And I think, somehow there's this idea that with science, it's all or nothing. But the fact is, people learn a lot more science, even if they don't get everything. And I think that's worthwhile.
So what about...
And I try to write my books, actually, so that you can gear it to the level that you're at. If you can't get all the technical stuff, you can skip that part.
Right.
But you can still get a sense of what we're doing. If you're someone who knows something and really wants to know how it fits together, the technical stuff is there.
So there's a lot of talk these days about STEM education in the U.S. and how America's falling behind. Spoke with Neil deGrasse Tyson.
Exactly. There's a lot of talk.
Well, there's a lot of talk. And it's interesting. I interviewed Neil deGrasse Tyson recently, and he said, one of the arguments for having a really robust space program is because it inspires people. And that, so back in the 60s and the 70s, there wasn't a lot of talk about STEM because people had something to be inspired by. Certainly there are things in biology to inspire people, but I think it's tricky. There's really not the kind of awe-inspiring stuff. To some extent, it's probably because there's not as much risk.
But I think it's also actually that there's sort of more awe-inspiring stuff. There's just so much stuff. Look at your Huffington Post page every day. There's a lot of stuff, and a lot of it is awe-inspiring. It's just we don't necessarily pay it as we have a short attention span. I think there is a lot of awe-inspiring stuff going on, and that's what I'm trying to explain it too.
Well, and is that one of your goals in writing the books is to kind of cultivate this sense of desire to learn about science?
That's right. And one way I described it is, sort of like, when you follow a sports event, if you know about the team, if you've been studying up on them, you're a lot more invested. You care a lot more. You understand the results better. You care a lot more. You enjoy the game more. And so I wrote these books before the Large Hadron Collider discovered the Higgs, the knocking heavens door, and it really was in part like that. And before I want people to say, what is it that we're doing? What are we excited about? So that when it happens, and I think it is much more satisfying when you have some sense of where it fits into everything else.
Right. Let me ask you, what is the most, I know you said this is not really the end-all and be-all for scientific research of the sort that you're doing. What is the most awe-inspiring scientific fact or discovery, let's say, of cosmology or of particle physics in, say, the last generation?
I am very bad at IST questions. I'd almost say that the most awe-inspiring fact is the fact that how many successful predictions there are, that this works, that we sit down and we this is in the last 100 years that we've understood the evolution of the universe. It's amazing. And you can put it, you can look at any one individual fact, but the fact that we understand that we live in this expanding universe, that we understand how nuclei form, that we understand what it's made of, that we can talk about dark matter, that we can talk about cosmological inflation. I mean, this is amazing that we can do all this.
Well, I meant to ask you this earlier, but can you give us a very brief description of this? Because when the universe, when the 20th century dawned, there was a very different idea of the universe, and there was no knowledge that the universe was expanding. Correct? I mean,
there wasn't even knowledge that we weren't the only galaxy.
Mm-hmm. I mean, that to me is one of the most awe-inspiring. Tell about the discovery that these dust clouds were not dust clouds.
Right.
That is the most amazing.
I mean, there's a reason they're called nebula.
But explain that story. Tell us that story.
Before, actually Edwin Hubble, who discovered the expansion, first actually realized that nebula were galaxies, or many of them were. And that's to say other galaxies distinct from our own, clusters of stars that are gravitationally not bound to us. And that itself is exciting, knowing that there's... Yeah. I mean, so we know there's lots of stars, then we find that there's galaxies, then we find that there's galaxy clusters. What Edwin Hubble also discovered, of course, very famously, is the redshift of galaxies that show that each galaxy is moving apart from every other galaxy.
Right.
And so, that's a major... I think a lot of the understanding of science that we have has to do with how things change, and that's pretty exciting.
Well, thank you very much. It's been a real pleasure speaking with you.
Thank
and
you.
Look forward to some more big discoveries soon.
Thank you.
Science Insider with David Freeman, the senior science editor of the Huffington Post, produced in cooperation with Robin Hood Radio, robinhoodradio.com on the web.